Hello my friends, welcome again. Today I will talk about a very interesting topic, and this is about distributed parameters. We will have an example which is transmission lines, but this will be only the setup for the broader topic of distributed parameters. In this case I will discuss how different is a lumped parameter model and a distributed parameter model. And in this figure we can see the idea in a wider sense. As you can see, in a more simple model of lumped parameters, all this transmission line will be modeled as if its characteristics were located in a single point, and because of that we will only have variations in time. So it doesn't matter if we measure anywhere, we use our multimeter or our measuring device. The only variation that we could see in this kind of model using a simulation tool would be a variation in time. You can compare this with the model shown in the figure below, in which the characteristics of this line are, or the parameters are distributed along the whole length, and this we can divide the whole length of our line into delta x segments, and if we take these segments arbitrarily small as we like, then we can work with the calculus to obtain very useful results. So in this case the voltage and the current will be not only time dependent but also space dependent, because now we will have a variation depending on the point when we use our measuring device. So in this case I would like to mention also that also the parameters could also be dependent, time dependent and space dependent, and this would complicate our model, and in fact this can be done, but for this video and for the sake of clarity I will stay with the constant value parameters along the length of these transmission lines. So these will not vary, and only the variation that we will see here will be because will be in the voltage signal and in the current signal. So these constant parameters will mean that our transmission lines will be the same material, will be of a similar uniform gauge, conductivity, inductance along the line, the whole length. So we don't complicate this analysis. So the next in the next slide I will show you how to derive a model of this. Okay, we will start working with this circuit using mesh analysis, and the first step will be to consider three meshes, and in each mesh there will be a current that I indicate with I subindex I2 and IO, but in this case I will use the voltage as an input, VI. Okay, so we will have this input and three elements in the first mesh, but the third element will be a capacitor that will have interaction with the second mesh. So here's the analysis. We start with the input voltage, and then we will have this inductor considered here with which is affected by the first current, and using the constitutive relationship of this element we will have a derivative of this current, and the next element will be a resistor, and finally this relationship, constitutive relationship, is very simple, is the Ohm's law, and the third element will be this one, the capacitor, in which we will have two currents that will contribute to the state of this element. So we will have first the influence of the first current, and then the influence of the second current from the second mesh. So we'll have this equal to 0, and that will be our first equation. Next, for the second mesh, we will have a similar case with the capacitor, and in this case the current I subindex I will be contributed in a positive with a positive sign, and the second current I2 will be with a negative sign. In this case will be storing energy. And then we only have another element more, which is this dissipative element, but we will use it as we will indicate that its value with the conductance, and we can see here that since the conductance is a reciprocal of the resistance, this will be indicated by I2 divided by G delta X. So this will be from the perspective of the first current, and we have the contribution of the current IO also with a positive sign, and that's our second equation. And finally, for the third mesh, we'll have this once again this element, this resistive element, or this conductance, if you can see it that way, if you want to see it that way. First with the influence of the first current I of the second current I2, and then with the influence of the output current IO. This will be our output, and of course there's a contribution of the voltage, output voltage VO, which we indicate here, and following the signs of this voltage, we'll have a negative sign on this one, and that will be equal to 0, and that's our third equation. So next I will repeat here in this slide our third equations, and we only need to follow some very simple substitutions and solve for certain variables to continue to carry on our process. And we will have here that from the third equation we can solve for negative BO, and we use that negative and BO because that will be useful for us, because as you can see in this on the right hand side of this equation, we have the same two terms in the second equation, which are indicated here, and we can put them inside this second equation, and that's what we will do in this step, and that's the result of that is our fifth equation, equation 5, sorry. And then we will do a similar step, because we will solve once again for VO in 5. So that's this solving here, and once again these terms will be useful for us because we can substitute them now in the first equation. As you can see, we go back to the first equation and substitute this expression here, and we will put there the negative VO, and the result of that is the equation 7. Now we have a simplified the result of that will be in terms of VI and VO. We can solve for this subtraction as we indicate in equation 8, and now we have this subtraction of VO minus VI, and on the right hand side we have only currents or expression involving currents, like this derivative of the current. So now we need to do a limiting process, because we don't want to calculate the whole segment, but we want it to be infinitesimally small. So we will divide that by delta x, which is what we do in equation 9, sorry, and finally we will have this limiting process here in equation 10, in which delta x will tend to 0, and the result will be now a partial derivative on the variable x, on this term in the middle, which will be equal to a partial derivative, but in terms of time, plus minus the expression of Ri subindex I. And now we only are in the last equation 11, we only arrange all those terms so they look better. I just separated the voltage from the partial derivative symbol, and I returned the notation for the dependence of position and time, but the equation is the same as in 10. So this will be one of our partial results, and we will have to keep that in mind for our next for a future step. Okay, now in a similar way we can have a node analysis in which we will use the currents. So we can imagine this circuit now as having an input, but this time the input will be the current. So in this first branch, which includes L and R, there will be a current I once again, and this we will have to make an algebraic sum of the currents. So in this case we have first the current entering this node, which I named alpha, and which I am separating here for the sake of clarity, but we can use it as we can view it as a single node. But then this algebraic sum will include also in a negative, with a negative sign, this capacitor, and we will be using here the constitutive relationship of the capacitor, in this case using the voltage of the node A, or more strictly the derivative of that voltage. So that will be the first outgoing current, and with a negative sign. And finally in this case we will have another outgoing current I2, and everything, this algebraic sum is equal to 0, and that's our 12th equation. And the next step, we will do the same with the next part of the same node. In reality it's the same node, but I'm just separating this for the sake of clarity. So we will have here an input current I2, and the outgoing currents will be G delta X times VA. Remember that this is a conductance, and we have an expression of the voltage here in this node A, and another element of this equation another term of this equation will be the outgoing current, the output current IO. So once again this algebraic sum will be equal to 0, and that will be our equation number 13. And I will repeat once again these two equations, because we will once again have to solve for some variables, and we will have to do some substitutions. And in this case, going from equation 13 to 14, we can see that we have isolated or solved for I2, and we have this expression that we can substitute in equation 12, as we can see here. And this is basically one we could do this in the one single step right from the beginning, but as I mentioned, I'm just doing this for the sake of clarity. So the result of this is equation 15, and now we can proceed to solve in the next step to equation 16, in which I've just separated the currents from from all those terms that include a voltage, and I'm just making this a subtraction of IO minus IO minus II, and on the right hand side of equation 16 I have the voltage and the derivative of the voltage. So once again I will do division by delta X, and this division will be once again part of a limiting process in which delta X will tend to 0, and as we can see here the result will be a partial derivative of I, and with a partial derivative of I and the variable X, and on the right hand side of the equation we will have a partial derivative with respect to time, and the last term will be simply an expression of the voltage times the conductance. And as we did in the previous part of this analysis, we will only arrange in equation 19 the results so it can look better, and we can make evident the dependence of these signals of these variables, its dependence on time and space or position or x variable. Okay, so we have here once again these expressions, and we will continue with our analysis now. So we finally reach a point in which we can relate the first and the second part of our analysis, and because of that I will need to repeat these two previous results. These are equation 11 and equation 19. I will need these because we will work with them and we will have to take derivatives in them so we can reach our final result. So in this case I will start with equation 11, and as you can see this equation already has some partial derivatives. So the next step will be to take a partial derivative with respect to the x variable. So in this case we will have here a second order derivative in the left hand side of the equation, and on the right hand side we will have some first order derivatives and some a mixed derivative which involves x and y, x and t, as you can see in the first term of the right hand side of equation 20. So we will keep this in the aside because we will now work with equation 19, and in this case we will have to take a time derivative or a derivative in the t coordinate, and in this case once again we will have a second order derivatives in the equation 21, and once again mixed derivatives that involves t and x, as you can see on the left hand side of the equation. So we need to connect these results. So we will take these highlighted elements and we will have to substitute them. As you can see, we have mixed derivatives, but the order in which the partial derivatives appear is different. But we must keep that in mind. But usually in physical systems this can be commutative, so we can work with it and we can assume that these are the same. But this is a mathematical thing that you should keep in mind, because it's not always possible to consider these terms as equal if you're being strictly mathematically. But in this case we can substitute this expression, and we will take the right hand side of equation 21 and substitute that in equation 20. In a similar way we can take, and the result is equation 22. In a similar way we can take the expression indicated by equation 19 and substitute that in the last term of equation 20. This is a less problematic term, and we will have the result here, and simply substituting without forgetting the r there, and the result will be equation 23. And now as you can see, all this equation 22 will be in terms will be a function of V, the voltage. So now we have gotten rid of the current. So far so good. Now the next step will be just to organize our equations and to take the second order derivatives to the left hand side, and in equation 24 we have the result, in which we also have grouped similar terms, as you can see in this red box. Finally we have in equation 24 we can even go further and make some assumptions, and in this case our assumption will be that we have no dissipation, and in that case the assumption will be that first, before that, I would like to mention that the same procedure can be done, and we will reach the same equation, but for the current. So the elements will be identical, but the function will be in terms of as a function of current of I. So these are very useful, and as I mentioned, we can make some assumptions about the dissipation of energy, and if we assume that R and G are 0, some elements are 0, multiplying the partial derivatives and the functions, and the result is this equation 27, in which is known as the wave equation. And we can further organize this by simplifying the coefficient LC in using the symbol U equals 1 over square root of LC, just to be a simplified notation. And as you can see, this can be organized in the following way, as shown in equation 29. And here it is, the famous wave equation, and this is very useful if you work with acoustics, electrical systems, fluid mechanics, and string mechanics, and all that. You will notice that it appears everywhere, and of course is not always you can have similar equations with dissipative terms, like when you have for example in acoustics, and your gas or your medium is dissipative, you will have extra terms. But this equation 29 is the wave equation as we know. So this is the same result applies for the current version of that in this case. So so far so good. I think that we have reached a useful result, and perhaps we can leave the expression for the solution of this equation for another video, and you can find this in my channel. And if you consider this useful, and if you like to find some content like this, look in my channel and like and subscribe and comment if you have any question. Thank you for your time. Goodbye.